Okay, so when I was covering this slide on DCGD theory and this iteration complexity result, I didn't highlight this assumption. It's here, but I didn't highlight it. This is true if you assume interpolation. What I mean by this is that the gradient of every single function fi at the optimal point is 0. Okay? Then this is true. Otherwise, you have a different result, but you will not get linear convergence. You get slower convergence. Or you can think of it as you get linear convergence, but not to the exact solution, to some neighborhood of the solution. There's two ways how you can think of it. What I want to tell you about now is that this assumption can be completely removed at the cost of changing the algorithm. And the algorithm is the Diana algorithm. That's what it does. It basically achieves something almost as good as this result without assuming interpolation, which means for completely general average of functions fi's, the optimum model could be such that gradients of fi's at the optimum model are arbitrarily different across these functions. Now, if you have overparameterized models, you tend to have interpolation. That may be one of the many explanations why overparameterization is useful, because then these simple algorithms are useful. Okay? But if you don't have overparameterized models, this is not going to be the case, and then you can either pay for the fact that you lose linear convergence, or you have linear convergence to a neighborhood, or you can run Diana algorithm, which looks like this. So this is just like DCGD. You have compression mechanism and any of these mechanisms that you have seen, natural quantization or sparsification and so on. These unbiased compresses with conic variance. But now you're not supposed to compress the gradient. You have to compress the gradient minus something. And then that minus something, you add it to the compressed vector. And now when you look at it, it looks really weird, right? Because why are we compressing? Because we want to reduce communication, right? Which means we will send this compressed message to the server. What about this? This is not necessarily sparse vector. Well, this is where this Diana update of this H comes in. Imagine that this vector is already owned at the beginning of the process by the server. When the server receives this compressed vector, it can multiply it by some scalar, add it to the message that it owns, and it will update this H vector on its own. So this Diana trick not only fixes the assumption, the interpolation assumption, but on top of it, you can implement it in a communication-free way. So this H, you don't have to communicate. You only communicate these compressed differences. Okay? So this is the Diana algorithm. Any questions? So the right way of thinking of this HIK sequence is that these are vectors that will converge to the gradient of fi at the optimal point. Now, why is that important? Because if you believe the algorithm to be convergent, then this will converge also to the gradient of fi at the optimal point, because xk converges to the optimal point, right? And these gradients are, let's say, Lipschitz, so they're continuous, right? So this difference converges to 0. But what happens if you compress a sequence of vectors that converges to 0 vector? The variance of that sequence goes to 0 because of this conic property, right? If V has small norm, its variance of the compressed version of it will be small. So that's where the power of the algorithm comes from. It keeps compressing smaller and smaller vectors, so while the compression is still, let's say, d to 1, the variance goes down. Okay? That's what it does. Okay, so now you have a similar theorem. Now these numbers 6 can be reduced to maybe like 4 or 3 point something. Let's not worry about the 6 and 2. These are small constants. And the idea is L mu is the same thing as before, Li is before, omega I is before. All of this is what you've seen, except now you have some Lyapunov function here which converges to 0, which implies that xk converges to x star and these hik's converge to the gradient of fi at x star. The Lyapunov function is basically just the square distance between these plus a multiple of square distance between these. That's what the Lyapunov function is. And now you can also think about this. What does this do? in terms of communication complexity, because we just counted the number of iterations. It doesn't mean anything. Okay, it means something, but not what we want. You can compare Diana to gradient descent, also by doing this division and computing the improvement factor. I'm not showing you the expression because it's a little bit more complicated, but trust me that it's always at least 1, and it's upper bounded by the minimum of d, n, and k max, and it could be as large as this. So again, the improvement can be huge, because if the condition number is huge, or n is huge, d is huge, if all of them are huge, the minimum will be huge. And potentially it could be in the regime where the improvement is really huge. Okay, so that's what Diana does. Now, the way you can think of Diana is that this is error feedback, but not the original error feedback that I will talk about that you know about, but this kind of error feedback specialized to unbiased independent compressors. And because it's specialized to these unbiased independent compressors, which is a smaller class than these biased compressors, you can do much better error feedback than if you do error feedback for the biased compressors. So you have very, very strong theory. And in particular, the theory tells you the method is much better. It's always better than gradient descent, and it could be much, much better than gradient descent. For error feedback, which those of you who know what it is, you don't get that effect. And those of you who don't know what it is, you learn what it is, but you don't get that effect. Okay. All right, so that's that. Now I'll skip this. And you can read some other sources on Diana. So it turns out that this was the first variance reduction mechanism for compression, but only for one node, not in a distributed setup. We didn't even know what we invented, actually. We're trying to come up with applications of this algorithm, and we didn't think of compression at all, okay? And then we realized, oh, we should do this distributed, and then we figured out the Diana algorithm. There's some extensions and so on. Okay, so you can accelerate this. So this trick of compressing gradient descent can be combined with Nesterov acceleration, and you get combined effect. So I will not go into details here, because the algorithm is complicated, and these formulas also don't look super nice, but you have the citation, you can read the papers. Here, I just want to point out, if you implement it in a setup where all these assumptions are satisfied, so these are not neural networks, these are problems where indeed you have strong convexity, L-smooth has exactly the same assumptions. So these are toy problems. But again, these problems are again just models. Then the acceleration is much better than Diana, which is better than DCGD. So this is DCGD, Diana is better, accelerated Diana even better. So indeed, you get that effect. So here, compression, acceleration can be combined for added effect. In the convex case, accelerated Diana doesn't work, but this Kanita method works, and that's the best method that we know at the moment, to the best of my knowledge. Okay, error feedback. What is error feedback? It started with this paper more than a decade ago, Interspeech 2014, Seiden and co-authors. One of the first papers, if not the very first paper, doing theory for error feedback was Sebastian's paper, Sparsified SGD with memory. And you can correct me if I'm wrong, but to my knowledge, this was the first paper that did any theory for it. And this is the paper I want to focus on here, because in some sense, this improved on what was happening before. Okay. So error feedback, the idea is that we want to work now with this big class of biased contractive compressors. Why? Because they work very well in practice. That's why. That's the motivation here. So if you do compression with this top K compressor, intuitively you capture much more energy or information in the vector than if you do rand K. So if things are not too bad in the setup, maybe this should work better, right? Okay. However, it turns out that if you apply DCGD to top K, the method breaks down. Okay? You cannot even prove any bound because there's no bound to be proved. This method diverges exponentially. And here is an example that we found in this paper 5-6 years ago. This is just three-dimensional example with three functions, and everything is strongly convex. And we have formula what happens at the k iterations, and you see exponential divergence. Okay? So error feedback just doesn't work with top k. In this case, it's top 1. So what's wrong? Yes?
So this example...
So not error feedback. Sorry, DCGD doesn't work with top 1. Yeah.
If If you assume that there exists a shared optimizer in the interpolating setting in which you motivated, one could claim that's reasonable. Does the example still hold? It doesn't seem to. Or is there another example which you can construct?
So this is a good question, and I don't know the answer right now.
Yeah.
I understand it. I don't know the answer. I know it even occurred to me at some point, and I just never even found time to think about it. So maybe. I just don't know. OK. So it doesn't work. Now what can we do? Well, there is a solution, this paper, which introduced error feedback. This paper from 2004. There's no theory in it whatsoever. It's a practical, empirical work. And the idea is this. And I will call it error feedback 14 because it was developed in 14. And there's this improved one, which was developed 7 years later, which I call EF21. Okay, so it was not called error feedback 14. It was either called error compensation or error feedback in the literature. I just called it EF14 to distinguish between the two. So it works like this. And this is on a single note. So if you have just a single note for simplicity, then you would compress the gradient at the single note. And at the beginning, you didn't have any error. So the E0 error, E0 is 0. So you just compress the gradient and kind of ignore for a bit that the gradient is multiplied by the step size. Just forget about that. It's like a technicality. So this is something just like compressed gradient at the beginning. But then there's this error, right? Because you sent compressed gradient, but you wanted to send this. So this is the error. This difference is the error that you caused by sending something compressed and wanting to send something non-compressed. And you remember that error. And next time you're going to be sending something, you add that to your gradient, and you try to compress that. And in this way, the error propagates, OK? And the correction propagates. So EF14 is just that algorithm. I mean, it's basically this algorithm, right? You always remember the error and add it to the next gradient. Then you compress again, remember the new error, add it to the next gradient, and keep doing that. OK, so that's it. And the distributed variant is basically the first idea how you would think of distributing this. OK, you just do this individually on every node. You put subscript I everywhere, and that's how it works. Completely trivial extension to distributed setup. However, there was an issue with this error feedback 14 method. The first issue was that there was no analysis. And then Sebastian came up with analysis. There was analysis. But that analysis in this pyramid of analyses was in that setup where this actually makes the method worse. It makes it convergent. It's not heuristic anymore. So it was a huge achievement, because before that, it was complete heuristic. Then it was not heuristic, but it made the analysis worse. And not only the result was worse than gradient descent, but under even stronger assumptions than gradient descent. So you get worse rate than gradient descent under weaker assumptions than gradient descent. So it's great that we have that, but it's not what you would want. So the question is, do we toss it away because it doesn't work, this trick? But in practice, it works wonderfully. So, and that gave the community the inspiration to think about this further. Something was clearly missing something. So, and that's what was fixed in this paper that I'm going to talk about, EF21. So this is Sebastian's paper, and there will be some other papers, yet another one, Sebastian's paper, and so on. And Anastasia's paper right here, and so on and so forth. So there's a bunch of works, and error feedback 21 solved these issues. And the simplest way for me to explain what EF21 is, now that I introduced Diana, is to show you how Diana differs from EF21, which we didn't know at the point of developing EF21. So we didn't know that. So this is Diana, written completely differently. And this is EF21. Do you see the difference? The difference is only in this lambda here. In Diana, you have lambda, and here the lambda is 1, whatever that is. It's just one scalar difference in 1 point. It's almost the same method. And you should kind of expect that it's almost the same method, because what is Diana supposed to do? It's supposed to be some sort of error feedback mechanism for these unbiased compressors. Okay, and error feedback is also error feedback mechanism, but for these biased compressors. It's supposed to fix that error. So it's almost the same thing, but not quite. Okay, and this is some generalization of both EF21 and Diana to this class of BV compressors, which I showed in that picture initially. Okay, so now this is a whole bunch of optional slides which I will just skip through. Yeah. Yes, right.
Is there like a difference between EF21 and Diana in terms of like robustness? Like are they like more robust to?
Yeah, so EF21 works provably for any biased compressor. Diana does not. Diana works for a subset of biased compressors, but those which become contractive after a scalar multiplication.
Right.
So EF21 is more robust, but the theory is much worse.
Right.
But only robust in the sense that it works with more compressors.
Right. Is there like a quantity that captures that, like some kind of like robustness ratio or like?
No, not that I know of. No. Okay, so now I skip all of this because now you know what EF21 is. I don't have to introduce it. So this is all optional. All optional, everything skipped. Okay. The only thing I'm going to show you that EF21 improves on EF, and you probably don't see it here very well. But anyway, even in practice and in theory. I'll skip through it. Here are some extensions of EF21. Okay, one thing that I want to say is this. If you compute now the improvement factor of EF21 over gradient descent, and you optimize over, let's say, the top K, the K parameter, just like we did with DCD and rand K, the optimal K was 1, and there was a huge improvement factor. Here, for every K, you get the same improvement factor, and it's 1. It's just the same. So basically, theory tells you if you compress with top 1, you have D times more iterations. Each iteration is D times cheaper. That's what it tells you. In practice, it's this orders of magnitude difference. But in theory, this is what you get.
Another quick question.
Yes.
Are these analyses that you're comparing in this particular setup assuming the interpolating setting or not?
No.
So is
No.
Okay, so
No. Error feedback algorithm doesn't have to assume interpolation, just like Diana doesn't have to assume interpolation because it fixes the interpolation assumption of DCGD
And
for linear convergence.
Has
let's
someone
say.
looked at it in the interpolating setting? Does this gap go away or no?
Again, I don't know. I didn't look at it. Okay, so then the all kinds of extensions. So this extension does the following. There was this decade of work, almost decade of work on error feedback, but none of those methods work with constraints or with the procs or with partial participation. There wasn't any theory of that type. The reason why there wasn't any theory of that type because it was difficult to do theory for EF14 because it was a strange algorithm. But for EF21, things became much simpler, also in theory. So this was suddenly possible. So we did some analysis with partial participation, with bidirectional compression. The server can compress and also use EF21 and so on and so forth. So these kinds of things with momentum and etc. This 3PC is a further generalization of these biased compressors and of error feedback. So have you heard of lazy aggregation mechanism? Event-triggered lazy aggregation. So I know that Sebastian has because I read his nice paper about it. So, was it joined with you? No? Okay. Okay. Look at each other. So, okay. I don't remember all the authors of all the papers. But it turns out that you don't need error feedback for lazy aggregation, whatever that is, because lazy aggregation is some sort of error feedback, but it's not error feedback 21. It's something more general than EF21, and it's an instance of 3PC. And error feedback 21 and lazy aggregation are both special cases of this 3-point compressor. Okay? So that's the story. And again, I would need maybe at least 5 minutes to describe. This is all I'm going to tell you. And this lazy aggregation is just the idea of I'm a client, and I will remember what was the gradient that I sent last time to the server. And if I compute a new gradient, and if the difference is not too large, I just don't send it. And I just send a bit telling the server, pretend that the previously sent gradient is the same. Okay, just use it. And only if the difference becomes too large, then I send again. So this is lazy aggregation. And it turns out you can prove convergence and so on, and you don't need error feedback for it because it is an error feedback mechanism, but it's not EF21. It's an instance of a generalization of EF21. So EF21 and lazy aggregation are two brothers or sisters or siblings of 3PC. Okay. Then EFBV is this generalization of Diana and EF21. And then actually this is very interesting, so I'll tell you this. It turns out we realized that EF14 in some sense was never supposed to be used as a error feedback compression on the clients. We figured out that in fact EF14 you should use it on the server, not on the clients, on the server. And there's just one server, not multiple servers. And you should use it to compress the model parameters, not gradients. And that's what we call EF21P. In fact, we developed EF21P without realizing it's completely equivalent to EF14 on the server. And then you should use a different error feedback mechanism on the clients, for instance, EF21 or Diana, or just use DCG under interpolation. And then what you can prove is you can actually get methods which work with bidirectional compression. So now the KAUST model would also include cost from the server to the clients. You can now include it. Why can you include? I mean, you could have included it before, but it wouldn't make any theoretical benefit. It would just not even benefit even without it. But now you include it and you can benefit. So now with this kind of an algorithm where you use EF21 primal version, which is equivalent to EF14 on the server, and something else on the clients, you can have a more accurate KAUST model, and you can benefit in communication complexity compared to no compression, or compared to just unidirectional compression. Okay, and so on and so forth. Okay, so here's one nice paper which used EF21P on the server and EF21 on the clients to train a foundation model over 500 megabits per second networks in practice. So this is empirical work which also contains some theory of the type where you bound things away. And here maybe last comment. If you use error feedback 21 with stochastic gradients instead of gradients, something bad happens. So the trick is not nicely combinable with one of these tricks in federated averaging, which is stochastic approximation. What happens is you have to use very large mini batches in order for the method to converge. You cannot use mini batch size of 1. But we figured out a trick with Ilyas and Sasha Turin. If you include Polyag momentum, it's all fixed and you can work even in mini batch size 1. So you have to add another trick in order to be able to work to combine error feedback with stochastic gradient, and there's momentum. So this is one of the very few rare instances in optimization where Polyag momentum actually has positive effect. This is very rare. Polyag momentum typically, whenever you look at any analysis of any algorithm, things just don't get worse or they get a little bit worse. Here it gets better. Just like, let's say, for normalization. So that's this famous paper. For normalized SGD, momentum helps. Okay, and there is extension to non-smooth optimization and improved analysis and so on and so forth. I will not comment on this. Maybe I will mention this work by, again, Sebastian on composite optimization with error feedback, some new approach. Our new paper on doing error feedback for muon. So I believe you know what muon is. Here the challenge is that this is basically non-Euclidean SGD with momentum, and it's not clear whether error feedback would work in that setup, but we made it work, even in theory and in practice, and so on and so forth. Okay, so now I moved to non-convex regime. All of this was strongly convex regime, and all of these methods have guarantees also in the convex regime, non-convex regime, beyond strongly convex regime. I'm just not showing you because we don't have the time for it. However, it turns out, if you look at the smooth non-convex regime, EF21 will have guarantees, but they will not better than gradient descent. In DCGD, we'll have guarantees to be better than gradient descent in the interpolation regime. Diana, better than gradient descent. You don't need an interpolation regime, but Marina will be even better than all of them, and that's why I want to show you this new method, Marina. For some reason, in the non-convex regime, there is a better method than all of these combined in theory. Okay, and that's Marina. And this is the same problem, and the assumption will be very simple assumptions. The functions have Lipschitz gradients, and the function is lower bounded. That's basically all. We want to find approximate stationary point with minimal communication, and again, it's the same model as before. Only the uplink communication costs anything, everything else is free. Why? Because we don't understand even this setup properly, so we want to understand it first. So the algorithm looks like this. Again, it's some sort of SGD, and the gradient estimator looks like this. So now you don't compress the gradient minus something like HK or GK is in error feedback, but the previous gradient, the one computed in the previous iteration. So you have to either remember it, which is not good because there's a lot of memory, or you have to recompute it, which is also not good because you have to recompute it. So that's that cost. So you compress difference of successive two gradients, and you add it to some GT, and you do this with very, very high probability, 1 minus P. And with very low probability, P, you actually have to send the full uncompressed gradient. So this is kind of hybrid method where you either send something, the whole thing, but very, very rarely, and most of the time, you send something compressed. And it turns out this estimator is not unbiased as the previous estimators, and the theory for this algorithm is much better. Now, if you don't like the idea that with some probability you send uncompressed message, then there is a different method called Dasha which fixes it, and also applies to infinite sum problems and so on and so forth. I will not talk about this. Now, I want to say something about Marina. I will not skip this part. What I want to say is that in Marina, well, in any algorithm, in DCGD, Diana, in all of these algorithms, what we want to do, we want to estimate average of some vectors. These are the uncompressed vectors that we want to send by the average of compressed vectors, right? But how do we do it with these unbiased compressors? Every client looks at its own VI, flips some coin, and chooses maybe rand K sparsification or quantization independently of the others to do the compression of VI, and the results, the independent results, get averaged, right? With top K, with these greedy ones, everybody greedily squeezes as much juice of VI as possible. But none of them cooperate, right? Either this independent process or greedy process, but it's not a cooperative process. And it turns out that Marina can benefit from correlated compressors. So here is now we're in this case of these AB compressors, which I will describe now. So the idea is this: the standard literature either independently or greedily compresses these vectors on its clients, but if you jointly collaborate, you can get theoretical effect and also practical effect. This method will be even faster than EF21 if these compressors collaborate. Okay, so what is the key weakness of these independent compressors? It's bad performance when these vectors are similar or identical. Let's just see that. Let's say that you have 3 clients, and the gradients are exactly the same vector, okay? Then let's use the rand1 compressor. So randomly, we choose the first element, randomly second, okay? What is the average of these compressed gradients? So this is the uncompressed gradient, this is the compressed gradient, right? What is the average? It's not the true average. There's an error, right? Obviously, right? There's some compression error. However, if we design them jointly in this way, we choose the first element, third, and second, or kind of any permutation so that they don't overlap, right? Then the average will be exactly the true average of the VIs. So the average of the compressed vectors will be the average of the uncompressed vectors. So how can we do this? Well, we cannot tell the first worker to always pick first component, the second, third, and the last one to choose the second component, because then they'll be biased throughout the whole process, and all of this information will be ignored. But if at every communication round you randomly permute these numbers, then it will work. And not only will it work, it will be better than independent choice, provably. So why is that happening? It's happening because of this inequality which we invented in this paper. So this is a new class of compressors which generalizes unbiased compressors in such a way that it introduces the possibility of injecting correlation. Okay? So remember, the whole idea is to estimate average of uncompressed vectors by average of compressed vectors. So why should we look at individual variances of individual VI? So let's look at the variance of the average of compressed vectors. So that's what left-hand side is, right? That's the really thing that matters, the average of the compressed vectors. Sorry, variance of the compressed variance of the average of the compressed vectors. And it turns out this is the right-hand side if you want to have good theory. So you have multiple of something like the second moment of the VIs minus positive multiple of first moment of the VI squared. Now, A has to be always larger than B because the right-hand side is non-negative. And if A is equal to B, what happens? If A is equal to B, then the right-hand side is multiple of the variance of those individual vectors VIs, right? What does it mean? If the VIs are the same, right-hand side is 0. Right-hand side is 0, right? If the VIs are the same and A is equal to B. So this example, what I showed before, I'm going forward, not backwards. This example that I showed before, this one, with this permutation, is an example of that, and it will satisfy this inequality with A being equal to B, and VIs are all the same, so right-hand side is 0, and that's why the variance is 0. So it's a special case of this very general class of compressors. Okay, now I will just jump through lots of stuff because I don't have to go through this. And I'll maybe return to one thing here. But what I will mention is that this is the theory of Marina under these AB compressors. And what happens is this. If the number of iterations is at least whatever is this expression, and there are 3 smoothness constants now, which I didn't tell you what they were. I will tell you later. Somehow there are 3 smoothness constants associated with this problem. And the A and B values appear. Then you have solved the problem. But it turns out that L plus minus smoothness constant is always better than L plus, and it can be as little as 0. It could be very, very small. And if you use these permutation compressors, then what happens? A is equal to B, so you get you erase the dependence on L plus. So you don't have that dependence on the bad quantity, and you get only dependence on the good quantity. What is this good quantity? It's something that we didn't know at that point in time when we discovered this, but it's something that's called second-order similarity. So we somehow figured it out that second-order similarity matters, and only then found out that there's literature on second-order similarity in some other areas, which have nothing to do with compression, but with local training, actually, such as Dane and these kinds of things, proximal point methods, and so on. So this method is basically a method which benefits from correlated compression and benefits from similarity. If you have a lot of similarity, this will have amazing communication complexity. Now, what is L minus? This is just smoothness constant of F. What is L plus? You can think of it as quadratic mean of the smoothness constants of functions Fi's. It's upper bounded by that. And this is similarity, second order similarity, but written in the first order form. So I'll show it here. This is L plus minus, right? This left-hand side is just variance of gradient differences, which is second order similarity. And if anybody's interested in this, I can go in detail into this. But the point of this is that if the functions, for instance, are the same, then this L plus minus will be 0, and then you get really, really good communication complexity. And very often, this L plus minus is much, much, much smaller than L plus. Okay, now I want to show you this plot. I want to show you this theoretical comparison. This is theoretical improvement, maximal theoretical improvement, on top of Marina, which uses independent compressors. So this is improvement from correlation. And it could be huge, square root of n or d over square root of n. So these could be really huge numbers, even many orders of magnitude. And Marina with independent compressors is much better than gradient descent, which you can kind of read off from this table, but I don't want to go into it because I don't have that much time. So Marina with independent compressors is much better than gradient descent. And once you correlate in this special way, it's even much better than independent compressors. So the effect is really huge. And then you would believe that if you have such a large theoretical effect, this should show in experiments. Here is an experiment. This is a toy experiment, just small, quadratic, 1,000 machines, 1,000 features. And this is the zero Hessian variance. We called it Hessian variance. We didn't know there was second order similarity. So they gave it the name Hessian variance. Yes?
So when you say it's better than gradient descent, you're looking at
in theory.
compressed gradient descent?
No, gradient descent.
Just gradient descent?
Gradient descent.
Okay, I see.
Gradient descent. So Marina with independent compressors is better than DCGD and Diana with independent compressors, which are better than gradient descent without any compression. So gradient descent is worse. DCGD, Diana are better with independent compressors than gradient descent. And Marina is even better than DCGD and Diana, and that's why I'm talking about it.
So do you know if it's better than naive compressed gradient descent under second order heterogeneity assumption? Because that will also benefit from having a lower second order heterogeneity.
I don't think so. It's very important that one has exactly that variance reduction that Marina has, right, that you compress gradient differences. And it's precisely because you compress gradient differences that the variance of gradient differences shows up, and that's exactly the definition of similarity. Okay, yeah, it's intrinsic in the method. The method has to be smart and do that, to benefit from second order similarity.
Okay, I agree with you.
Yeah. So that's not possible. And here, what I'm running is an experiment where I run. This is Marina with independent rand K compressors, and the best K is chosen. No, this is not K. Sorry. This is some multiplier of step size. We chose the best step size multiplier. Okay. But this is the best K for rand K. This is top K. So this is error feedback with top K, the blue. And this is permutation compressor. So you can see that permutation compressor is even better than error feedback, and then Marina with independent compressors. So what is very interesting is this, that Marina with independent compressors is already much better in theory than gradient descent. And gradient descent is exactly identical to error feedback 21 with top K. But they are almost identical. There's a small difference between these two lines, blue and red. So we're really missing something about EF21, really missing something. But perm K is better. And the theory for perm K also shows that it's much better. Okay, so you can think of this Marina method as some sort of the right way of doing error feedback in the non-convex smooth setup where you really have the theoretical effect. There's some more examples here where we show that as you get less and less similarity, the benefit starts shrinking. Okay, so this really shows the theoretical effect is there. Some other example, okay, doesn't matter. So I want to skip through this. Here are some extensions. I will not talk about them. Okay, so now bidirectional compression. We now want to have the KAUST model where the downlink also costs something, but not the same amount as the uplink, because it doesn't make sense, right? Maybe the downlink is cheaper than the uplink or more expensive. So you should put some cost to it. Now with this model, there have been some papers, but this is the first paper which showed some theoretical benefit, but only for some very limited compressors, some quantizers, actually for natural compression. Here, this is type of analysis where you get worse result than without compression, but you have a bound. So it's not a heuristic. Same thing here. You get worse result with bidirectional compression. However, here you get better result for any biased compressors. This was the first paper where in this model we can finally design an algorithm in this KAUST model where in bidirectional compression you do better than without compression. But it took time to design that algorithm, and we had to figure it out that the EF14 should be run on the server. And once this was figured out, then we got some other ideas how to do it. And here are these other papers. And to the best of my knowledge, these 4 papers are the only papers which consider this model, KAUST model, and where you have algorithms where you can benefit under that KAUST model. Every other algorithm that I'm aware of doesn't benefit. Okay, so just an interesting thing. Maybe I mentioned this one paper. In this paper, what we do is the following. The server compresses the model, but doesn't send the same compressed model to all the clients. The key idea in this paper is that you should compress the model multiple times and send different compressed versions of the model to different clients. If you do it independently, you can benefit by, if I remember correctly, square root of n in communication complexity. If you do it in this perm-k way, in a correlated way, you can get additional benefit of a square root of n. So you can do this trick, which I'm not aware of any algorithms of that type, where the server is supposed to just send one model to everybody, but instead it compresses it in multiple ways and sends these different compressed messages, versions of the model to the clients. And you get theoretical benefit from it. Okay. And here in this bicolor, this is the first combination of in the bidirectional setup, also with local training, and you get the benefit. So now even local training can be counted. So here you can see that if you, let's say, run, if you count the number of bits sent from the workers to the server, then there is no difference between Diana method, which doesn't compress at all at the server side, right? It only compresses at the worker side. And our new method, this yellow method, which does Diana on the workers and EF21P on the server. So the extra compression at the server side doesn't at all slow down, affect the number of bits sent from the workers to the server. But it hugely affects the number of bits sent from the server to the workers. And that's where the benefit is coming from. Okay, so this is probably the last part of this compression business. It turns out you could try to think of compressing hashing. So this is somehow towards communication efficient second order methods. Of course, we don't know how to implement this at scale, but bear with me and just imagine that communicating gradients would not be the bottleneck, and you want to run some kind of a Newton type method, and then the Hessians are the difficulty. What can you do? You compress the Hessian with some bias compressor, and then you run EF21 to fix for that error. It turns out that works. And it not only works that you get some bound, but you get a bound which is strong. And by strong, I mean this. You get a local convergence bound, because Newton method converges only locally, unless you globalize it. We didn't in this paper. But the local convergence rate is independent of the condition number, which is not true for any first order method, right? First order method always depends on the condition number. But Newton method has local rate which is independent of condition number. And this compressed version of Newton method also doesn't have any dependence on the condition number locally. Now when you implement it, and this is the communication model, this unidirectional one, we ignore everything else. We only count the number of bits sent from the workers to the server. And we compare it to all the previous methods that you have seen before. Diana, accelerated Diana, gradient descent, and some other methods. This new method wins, which is very surprising. So this kind of proof of concept, then if memory was not the issue, because you have to store these Hessians, or the computation of the Hessian was not the issue. Of course it is. It costs a lot. But if you ignore all of those things, then this can be actually even many orders of magnitude faster than these first order methods. But these other things do cost something, and that's why we don't use these kinds of methods. Okay? But if you had such a computer, it would work, yes.
Can these methods be implemented with Hessian vector product oracles, or that loses the geometry?
They can. There was a paper by my former PhD student who did exactly that. That he would be just doing these kinds of quasi-Newton kind of things instead of the exact Hessian.
And empirically they retain?
Yeah. They also have some theory, and empirically it works, yeah. So, so we extended this to partial participation and stochastic approximation, all kinds of other things in this paper, Fed and L, where we're trying to make Newton-type methods applicable to federated learning. But of course, this is all proof of concept. This will not work in any industrial practice because we ignore everything that matters except for one-sided communication. So this is where we are. Okay, that's it. And I will start. So we finish at 12, right? Roughly. So I will then start this part. There was a question? No. Any questions about what we've done? All good? So I didn't cover everything about compression, but I hope you have some idea about what's going on. And now we will ignore compression. We'll not talk about compression at all. It will show up at some point, even in this part, in a surprising part. But now we will ask a very different question, which is this. What is this local training business all about? What's really going on? And I kind of mentioned one possible answer to local training, which is if you think about this personalized formulation with this lambda or this Flix one, then the natural SGD actually accelerates if you have a lot of personalization, which is some sort of a generalization result if you think about it. But now we will not think about these formulations, we'll just talk about this original formulation and see what happens in that case. So the most basic local training method is distributed, well, not local training method, is distributed gradient descent, which you can think of as doing this. This is just a funny way of writing down gradient descent, nothing else. This is just gradient descent. You receive the model from the server, take one gradient step. Everybody takes gradient step with respect to their own function, f1, f2, f3. And these three models are now different. They are sent to the server. And these models are averaged. And if you do the algebra, this is just one gradient step, right? And now this xt plus 1 is sent back to the workers. Now we will work with the model, COS model, that all of these 6 arrow cost. So not unidirectional, bidirectional. And nothing else costs. So the work here doesn't cost, the aggregation doesn't cost, only the arrows cost something. And what people found out some time ago, and I will cite the literature, is that very, very simple trick can make this much more communication efficient. And the simple trick is don't take one local training step, but take multiple local training steps. So let's say capital K. If you do that, this is no longer gradient descent, and it's called local gradient descent. Now, the brief history of it is, so we wrote this paper where in the introduction, we somehow came up with this classification of these 5 generations from theoretical point of view. And the first generation is when this trick was discovered. And it was discovered in these 3 papers independently. So this is the famous one, most famous one, by Brandon and co-authors. But it was discovered even before in these other papers, exactly the same trick. And one can even go back to the 90s of thesis of Solodov, and in some form one can say that it was discovered even there. So here, practitioners found out, you do this, you fine-tune this K, and you can have 10 to 100 times fewer communication rounds than with GD. No reason why, just empirical evidence. And this is what you would find out if you run these experiments. So if you do one local step, and this is for beautiful L-smooth strongly convex function, you get linear convergence, but it's slow compared to if you take 2 local steps of 4 or 8 or more. The more local steps you take, the faster convergence you get, but the sooner you get stuck. Okay? And at that point, of course, there was no explanation, but this theoretical explanation for this phenomenon, but practically it's very clear that if you want this kind of accuracy, you shouldn't take one local step, you should take more local steps. The question is, what's really going on? So the first theoretical approach to this problem was to assume some sort of similarity between the functions. Why? Because if the functions are the same, right, then everybody should just take k infinity. The functions are the same, so these are the same problem. They don't have to collaborate at all, and everybody solves the problem and it's over, right? So by extrapolating from this some kind of continuity argument, if the functions are not too different, then maybe taking k bigger than 1 should help. And if you follow that intuition, you can turn it into mathematics, and that's what was done in the second generation of papers. So this is by Ginger and some other papers. These are not all of them, but these are some of the early papers. Okay, and there's some measures of similarity of this type, this strong growth condition. However, this assumption had to be made, this similarity assumption, which means that if the functions are allowed to be arbitrarily dissimilar, this was still a heuristic. Maybe it doesn't work, maybe it diverges. So in this third generation of theoretical approaches to this, and this is something where we have contributed to it, so these were the first papers on local GD for heterogeneous data, we proved that no, it's not a heuristic, the method will converge. But you don't quite explain why it's better. So in some sense you do, but not satisfactorily, because you get rate which looks like this, but the rate is the same as gradient descent, and you converge to some neighborhood. It's not faster than gradient descent. Okay, so then the fourth generation was trying to fix this convergence to neighborhood. How can you avoid getting stuck? And this is where, again, Sebastian with Cypranid and others solved this problem, and then we contributed to it too, and some other people, where they came up with the drift reduction technique. And the idea is, the high-level idea is this. Don't minimize Fi when you do local training. Don't do that. Minimize some sort of perturbation of Fi. It's something of that type. It's not good to minimize Fi. Minimize some perturbation of Fi and do local training for that. And then they change the perturbation next iteration, next communication round, and do it that way. And if you figure out the perturbations correctly, then this behavior of getting stuck will disappear while retaining this linear convergence. So that's great, except if you look at the analysis. So this was the best analysis at that time, just a few years ago. But even in this analysis, you don't get better communication complexity than gradient descent. So this is why I'm mentioning this hierarchy, right? There's reason, because this driving force behind this theoretical analysis. So this was the best that we knew at this time, but still, we're basically at the same level as EF21. It's the same as gradient descent, no better. Okay, no effect. This is in the strongly convex setup. So in the non-convex and convex, things are a little bit different. I'm focusing on this. Okay, and this is how it works. Local GD gets stuck, but these new methods such as scaffold or local gradient descent star, they don't get stuck. Okay, so you fix this getting stuck, but you don't explain why it takes 10 to 100 times less communication rounds than just gradient descent. And this is what the fifth generation of local gradient descent methods does. It basically shows that local training is, if done properly, is a communication acceleration mechanism, a provable communication acceleration mechanism, but not of Nesterov type. It's a different communication acceleration mechanism. And in the strongly convex case, this is what happens. This is the number of communication rounds without local training, or methods that do local training but are in this fourth generation, and those that are in the fifth generation. So just like Nesterov acceleration, you go from condition number to square root of condition number, but the acceleration because of local training. And this was done in this paper with former students Konstantin Mishenka, Grisha Malinovsky, and with Sebastian. Okay. So we're very happy, so we put 3 exclamation marks into the title. Yeah. You still remember, Sebastian, how we're on Slack discussing last minute the title? Okay, good. So that's what's going on. And once we figured this out, so this was the first time we saw the light after many years that, oh, this is actually accelerating things. Now we see what's going on if you do it properly. Then of course, we were emboldened and tried to see, is this combinable with other things? Can we think of some more complicated cost models? Can we, I don't know, add partial participation or not? Can we do bidirectional compression, or can we do compression at all? Can we do all kinds of other things, okay? So can we do it on a network, on a connected network, and these kinds of things? So, we then came up with answers for all of these things. And I will not go through these papers in details. Instead, I'm going to focus on this one big table. Yes, Zaid?
So is there like a high-level intuition of why
Yes.
like this perturbation is like, someone
Yes.
has an equivalent?
Yes, I have slides for it, but I will tell you right now. But I will tell you now, okay? So this is really what's going on. So we had to revisit proximal gradient descent as a method, because gradient descent can be written also as proximal gradient descent, where the prox just tells you, it's a constraint which tells you that the variables have to be the same at the clients. That's a linear constraint. And when you do proximal gradient descent, that's actually gradient descent, okay, with this prox. So when you take gradients with respect to the function, there's like a local gradient step because the xi's are different. And when you do prox, there's communication and averaging. So what we have to figure out, we had to decouple, we had to do some sort of important sampling in prox gradient descent to do prox less times than gradient. So we basically figured out that you can skip the prox for many, many iterations without this at all affecting the number of iterations. So proximal gradient descent is fundamentally not the right method. You can do prox much, much less often, and it doesn't affect the number of iterations at all. It just affects the number of proxies. And you get square root of the number of proxies that you had before. That means you get square root of that number of communications. That's really what's behind. So it's a revisiting of proximal gradient descent. Okay, so that's what proxkip does. And then we asked, for instance, question, is it really important that the local training method is gradient descent? Because in proxkip, you take local gradient descent steps. Can you use some other solver, SGD, ADAM, whatever? In this paper, APDA inexact, we showed that you can do any solver. It doesn't matter what solver you use. We just tell you this is the problem you solve. You can use any solver. So now we know that it doesn't matter what is the local solver. All that matters is solve this problem. And you can use any. You can use Muon, you can use ADAM, ADAM, whatever you want. So that's what is done. Then this is very similar to, let's say, what the FedProx did, right? FedProx is a very famous algorithm. It basically said, use any solver to compute the prox of f. But I will have a slide on FedProx later on. So here, in this VR proxkip method, we found out that if you replace gradient descent as a local solver with variance reduced SGD, then you can get a better, at even more complicated and better cost model, which includes local computation too. Before, it was not possible to include local computation in any of these analyses of any previous papers. This was the first paper in which we realized that you can account for the local computation, add it to the cost model, and if you change a local solver from GD to variance reduced SGD, you provably benefit. So that's what was done here. In this rand prox paper, we discovered something very, very strange, which we had no clue at all, which is that proxkip is nothing else than a special version of applying EF21 to the prox of some function in a more general algorithm. This is very abstract what I'm saying, but there's a close connection between EF21 and this local training. And the connection is that local training is EF21, but applied to a special compressor which is applied to a prox operation. So when you think about SGD, what is SGD? You're lazy to compute gradient, so you compute stochastic gradient because it takes less time, right? But this has some issues. Like SGD will not converge anymore to the exact solution, but it will converge with fixed step size to a neighborhood of the solution. Or you have to start decreasing the step sizes. But you can do variance reduction, it fixes it, right? Now, did anybody think about being lazy on procs. How can you be lazy on procs? You can be lazy on procs by computing procs inexactly, right? Those of you who know procs is, right? Minimization of f plus quadratic perturbation. That's procs of f. You can be lazy that way, but you can be lazy in another way. You apply a compressor to procs. You compress the procs, and the compressor could be this type of compressor. With small probability, the output of the compressor is the input. With large probability, the output is 0. And if you scaled this properly, it'd be unbiased. This is kind of like 0-1 type of compressor. And what does it mean? You either evaluate the procs or not. That's what it means. This is a compressor. It's actually unbiased compressor. You can apply error feedback 21 to it. If you apply to it, you get proc skip, which we didn't know when we developed proc skip because we developed with different intuitions. But that's what it is. So local training is nothing else than EF21 applied to very specific compressor applied to the procs in the prima dual Davis gene splitting algorithm. Yes?
Confused by the second row.
Yes.
You said you can use any local optimizer,
Yes.
including SGD.
Yes.
If I do that, then how do I get the same communication complexity with better local training steps? What happens to
So
the noise
we're
step?
better, okay. Because we also give 3 examples of 3 particular local solvers. One of them is GD, okay, that's the classic one, but one of them is accelerated GD, and one of them is this Kim and Fessler optimal gradient method for minimizing the norm of the gradient. And what you get is that none of those choices affect the number of communication rounds, but they affect the number of local training rounds. In proc skip, you have to take a square root of condition number of local training rounds. But in this method, you can take smaller roots, like fewer, even fewer local iterations. You can save on local training while the number of communication rounds is the same.
I guess you said you can use SGD, which I don't.
That was in this 3rd row, not in 2nd row. In 2nd row, we use these three methods as a special case, but you can use any method. So here you also can model the local computation, you can get theoretical benefit. And that's because we understand more deeply what's going on. So this is a very high level. Of course, I can't really go in detail through all these papers, many papers, right? But this is what's going on, really.
So one more
Yes,
thing.
yes.
So the intuition that you mentioned about skipping the proximal
Yes,
steps.
yes.
Is strong convexity critical to this, or
It
is
is.
there a way to?
In the paper, we only have strong convexity, and just very recently, we solved the convex case. And non-convex case, it has to be something very different. We don't have a clue. But in convex case, you can also get it, but we only recently solved this.
And you get like a similar.
We get like 1 over k
acceleration
squared.
effect with the convex case.
Yeah. But for a long time, we didn't know how to do it. What is grad skip? Grad skip is this idea that in local gradient descent, everybody takes the same number of local training steps, right? I told you, take k steps of gradient descent, take k steps of gradient descent, and so on. Why? Why the same number? What if some function is not very important? Why should you take the same number of local training steps? So we ask the following question. Are you able to do fewer local training steps than what proc skip does without affecting at all the number of communication rounds, but with decreasing the number of local training rounds for workers that have nice functions? And the answer is yes. That you don't have to take square root of condition number local training steps as here. And this L here would actually be the max of LIs, the worst of the local smoothness constants. And here in grad skip, we basically say it's square root of Li over mu. So if some Li is smaller, you do fewer local steps. Again, that means you can benefit, you can bother the workers less while getting the same communication complexity. So that's theoretical effect, not just empirical effect. Okay, that's what happens there. What happens in compressed CAFNU, we ask the question, can you combine local training, which will give you acceleration of communication, and also compression from all of this, we have seen all these compressed methods, right? Can you combine them together, but not just to have a method which you implement and see what's going on, but can you prove that these two effects multiply. That it's better method with combination than without. And yes, this is the first paper that managed to do so, this one, compressed CAF-nu. But in compressed CAF-nu, we did it only for very specific compressor. We couldn't do it for all unbiased compressors. In local DL, we do it for all unbiased compressors. In 5GCS, we solved the problem of accelerated local training and partial participation. We couldn't do it for ProSkip. We tried, we failed. We couldn't make ProSkip work with partial participation. If we did, we lost the acceleration. But then we figured out how to do it in 5GCS, which means 5th generation client sampling methods. You can do client sampling and have acceleration of communication. So we start combining and thinking of more accurate models. Okay? In bicolor, there's the first method which does accelerated local training and does bidirectional compression. Any questions? Yes?
So as far as I know, for a bunch of these methods, you need these extra control variates or
Yes.
some sort of memory on the clients.
Yes, absolutely. Absolutely.
In kind of like practical scenarios, there's a lot of...
Absolutely. So here, the game we play is that we come up with some cause model, which is going to abstract some things away. And those, we just say we have, like, I don't know, infinite memory or whatever, right? We just don't get bothered with those things, because if we get bothered by those things, we cannot progress here. But these things absolutely matter. And this is why it's very difficult. Well, it's impossible to close the gap between theory and practice. Everybody talks about this, but it's impossible. But we can get a little bit further. We won't be ever able to fully understand these super complex things that are happening in practice. It's impossible. But it can give some guidelines. So once you start having yet another consideration, which I mentioned in the overview at the beginning, let's say the memory issues, then you cannot do some of these things or any of them. Suddenly, you cannot do that, right? You have to do something else. But maybe this can give inspiration for fixing it somehow with some intuition, some trick. Maybe they would be on analysis, but it would be useful. Yeah. I'm not claiming that any of these things can be just taken and applied like they are. They're all some models.
My question was just, to the best of your knowledge, is there any accelerated method that doesn't require stateful clients? So like some sort of keeping track of an extra variable or something like that?
Well, you mean in the convex case, the strongly convex case? Because in the non-convex case, we cannot really talk about acceleration, right? Mm-hmm. So let's talk about convex or strongly convex case. Well, the problem is you cannot do acceleration without variance reduction. That's because acceleration is not combinable in exact gradients. There's a nice paper by Nesterov and Glinier and Devil there about this. But as soon as you need variance reduction, you need states. Okay, then there's momentum variance reduction, which is some sort of something between variance reduction and no variance reduction, something in between that is a little better in that sense. But unfortunately, it seems like it's not possible to get everything. But I don't have a proof of impossibility. But
right. But for example, like you could get some sort of variance reduction in kind of like the aggregated gradient, not in the local gradients.
Server variance reduction.
Yeah, server variance reduction, but maybe that. Anyway, maybe that's for.
Yeah, maybe, maybe, yes, maybe. Yes.
I'm curious. So this is taking advantage of the data to accelerate descent. And this is maybe going in the direction of kind of grad skip, but maybe going a little beyond it.
Right.
Can you invert this and say, when I'm not making progress, I can identify it's because I have outlier, something that breaks, Lipschitz constraint, something that where you can identify if I either, for example, hold out this subset of users, I'll make far better progress, or this is a subset of users that represents an entirely different, a set of French speakers that are in some training data and you're learning German, for example. Is there a way to sort of take these insights but go the other way and say, I'm not making progress and it's because of this property of the data and I can use that diagnostically?
I didn't think of it, but it makes sense. The question makes sense. And,
It seems related to
that's
GradSkip, maybe
that's
going beyond
exactly what I hope that this will be useful for, that one can use some intuition out of this to go beyond the math and the theory to implement something practical. And here the message really is, if the smoothness constant is small on some client, that data of the client is not important and fewer steps are needed. Now, how to detect that? That's a completely separate question. Any method that can detect it, even heuristically, should work. So here, this is just completely artificial problem where one worker has smoothness constant 10,000 and everybody else has smoothness constant between 0 and 1. And then in ProcSkip, everybody would have to do basically 10,000 iterations if the strong convexity constant is 1. That's too much. And here, GradSkip, if you look at it from communication around perspective, does exactly the same as ProcSkip. It doesn't, it's as fast an algorithm from communication perspective. So if communication is the only thing that matters, they're indistinguishable. But if you look at local computation, there is a factor 15 difference. We bother the clients 15 times less. There's an order of magnitude. 15 times less local work is needed for GradSkip. And this is a theoretical fact. I can play with this. I can choose this factor to be arbitrarily large, right? I can just by playing with these allies. So this provable effect, not just empirical effect. There's not answer to your question. I'm just explaining now the GradSkip. The question is how to identify the smoothness constant. Of course, if you have a problem which is non-smooth, then none of this applies. So the world is difficult. Yeah, so maybe one last thing. So this is what I mentioned before, which is there is this primal dual Daviesian splitting method, which we developed with former postdoc and some other co-authors some years ago, motivated by Daviesian splitting. And if you look at this method, RandProx is nothing else than the same method, but you apply compressor to the prox and do EF21 for it, right? Because you subtract U, you add U, and this is the compressor. That's it. And that's RandProx. And if you specialize the G function and H function and F function to something specific, you get exactly ProcSkip as a method. So EF21 is related to local training super deeply. Okay, we should take a break because I'm eating into your lunch. I apologize.
You just store it on the server and add it into